First of all, I should thank the organizers, Subhro and Sergej, for this, for organizing this nice workshop and for inviting me to speak. And I should also thank you for staying to the end of this this workshop. Okay, so I'll be talking about quantum many-body dynamics. Which is sort of I think a bit different from what you have heard of in the previous talks in this workshop, where people were focused on equilibrium properties and ground state properties, and I'll go through what the difference is. And ultimately, what I want to get at is how do you think of symmetries in quantum many-body dynamics, which appears to have some connections to the generalized symmetries that you have heard about. So just to set the stage, in quantum many-body dynamics, at least people are so far simple-minded. There are no categories to begin with. So we have a regular Hilbert space where you have some degrees of freedom, which are you can take as, like, say, spin half degrees of freedom. And then we are interested in, of course, local Hamiltonians. So the Hamiltonian is sum of local terms, say J plus 1. Right? And for concreteness, I'll just focus on one dimension, but you can imagine generalizations to higher dimensions. And then all of these Hamiltonians, you can, again, for concreteness, you can imagine they're expanded in terms of these Pauli operators, xj, yj, and zj. And yeah, so these set of Pauli operators or strings of Pauli operators, like you can imagine some strings of this form, like where these are identity everywhere, but then you have non-identities only in some local region. These are referred to as Pauli strings, which of course all of you would be familiar with. And then, so the idea is really, as I said, as the word says, it's to start with some simple initial state, which can be like a product state. So for example, just take some configuration of spins, and then study the dynamics of this initial state under the Hamiltonian. So this is just the regular Schrodinger evolution. So I have my time evolved state, which is e to the minus iht psi 0. Okay. And then I want to sort of deduce properties of this time evolved state, like things like correlation functions and so on. So now there is so you know that if your Hamiltonian is sufficiently generic, so if I, in practice, if I just start with a simple initial state and evolve it, there is this phenomenon known as thermalization, which is sort of like the class, there's also, which is the analog of the classical version of thermalization, where you start with some nice configuration of balls in a stadium, and then you just, each of these balls have some random velocity. The system thermalizes in the sense that in the end, after a long time, all of these balls are sort of arranged in a sufficiently random pattern. So there is no obvious pattern in their dynamics. So there is a quantum analog of that, which is the sense which says that after sufficiently long time evolution, this psi of t is almost a random state. So I'm putting random in quotes because it's not truly random. But for all practical purposes, this is some very complicated state in the Hilbert space. And so the idea is, like, if this Hamiltonian is generic, so you just pick a random local Hamiltonian, any simple initial state would evolve to a complicated state at late times. Okay, but then there is also this notion that this random state, somehow all of your theories of thermodynamics should apply at late time. So by a thermal state, so this random state is also called the thermal state. And there is some idea that thermodynamics should apply to this late time state. So what does that exactly mean? Also, if you have any questions at any point, just stop me. Yeah. Yeah. Yeah, I'll get to the precise definition of temperatures, but then if I just take some configuration of spins and then just take some random a generic spin half Hamiltonian and evolve it, the state would be at infinite temperature, but I'll get to the precise definitions in a bit. Yeah. Yeah, exactly. So that's the quartz, right? So it's a random in that it's sufficiently complicated that you can treat it as a random state. Right? No, I mean this is the entire quantum system. So I should maybe all of this is an isolated quantum system. So there is a Hamiltonian. It's not coupled to anything else. And then this is what I will describe as the theory of thermalization of isolated quantum systems. So I just have one Hamiltonian, and this is the full system. Yeah, so there is a sense in which this thermalized, which I will describe now. Yeah, but the idea is like there is some notion of a temperature of the state, which basically controls all properties. So I'll make that clear. Okay. Right. Yeah. So the way this final state is thermal is in the sense that if I look at the expectation value of any local observable, so say I have some operator O, which I'm measuring in this final state, this should look like as though I'm doing thermodynamics on this operator. So there is some e to the minus beta h O of A divided by the partition function. Okay. Yeah, that h is the same as this h. So it is as though that there is, if I start with some initial state, there is just one parameter here, beta, which controls the late time expectation values of local operators. So it's important that this is local. Right? Yeah.
Assume that the energy distribution of the initial state is not too broad. And
right.
How do you ensure this if you don't know
what the initial state is? Yeah, that's a good point. So what happens is that if your Hamiltonian is local and your initial state is simple, like it's a product state, then you can actually show that your initial state has a low variance in energy. Right? So it doesn't have a huge spread in the spectrum. Okay. But I'll not go through those proofs because that would be like a separate lecture, and I want to sort of just give you the idea of and then connect it to symmetries. Okay. Yeah. Oh yeah. Yeah, that's the idea. Yeah, those would be symmetries, for which this would not be true. But I'm now thinking of generic Hamiltonians. There are no symmetries of the Hamiltonians, and then under such Hamiltonians, what happens? And that the Hamiltonians that thermalize are the ones where you don't have any kind of symmetries, and I'll be more specific in a bit. Okay. Yeah. So I'll get to how you define the temperature. I mean, the energy is constant, right? Like so. Yeah. Yeah, so you can think of some distribution of energy in the system and ask how that is redistributed. Yeah, that is one of the consequences. But what I'm saying is just that local operators have this kind of a behavior at late times. There are fluctuations which are small, which again, there is some functional form of these fluctuations, which I will not get into, but this is the idea of thermalization. And yeah. Yeah, so small in it's suppressed by 1 over square root of the Hilbert space dimension. And so if you take, so the Hilbert space dimension is something like 2 to the L. As you take larger and larger system sizes, this is asymptotically true. Right. Yeah, that's the idea. Look, as long as your H is generic, and I'll be more specific about what Hamiltonians, for what Hamiltonians this would hold. Okay, so there is one parameter beta here, but okay, so just for information, the way you specify beta is to just, so I had my initial state psi 0. I can define some energy of this initial state. And then just solve for this kind of an equation. One way of thinking about this is that, so there is some energy for this initial state, which is the same energy for the time evolved state, because the energy doesn't change under this Hamiltonian. And then you can also compute, because the Hamiltonian is also just a sum of local operators, you can just plug this into plug the Hamiltonian here, and then you can compute this. And so for any initial state which has energy E, I can associate a temperature beta, right? And then the idea is, once I determine this temperature, all local operators should satisfy this equation, right? And this is sort of the basic idea of thermalization. Okay, so but in this talk, I will not be dealing with this temperature, and we will actually just be setting beta equal to 0, which is also called as infinite temperature, where things are much easier to think about. And what infinite temperature means is that this equation simplifies a bit. So you have so you have this expectation value is just the trace of this operator OA over the Hilbert space dimension. Right? So this is sort of like, the idea is like at very late times, you just average this operator over the entire Hilbert space. So you should really think of this as an average over all of Hilbert space, right? All states in the Hilbert space, and then the late time expectation value should be something like this. Okay, if beta equal to 0, which in practice you just take a random state, and it will very likely be beta equal to 0. Okay. Yeah. So suppose all of these things hold. So there are some consequences for things like entanglement and so on. So I'll just briefly describe those. So if this kind of an equation should hold for all local operators, then you can also make a statement about the reduced density matrix. So suppose this is my system, and this is the local region A for which this equation holds. Then what you can also say is that the reduced density matrix of my final state, so suppose I define the density matrix rho of t, which is psi of t, and then take the reduced density matrix. So there is some A and A complement, so I trace over A complement. So this reduced density matrix is a reduced density matrix on the subsystem A. And the idea is that this reduced density matrix should again look like e to the minus beta h traced over A bar over Z. I mean, this is not a very precise, it's very hard to make these statements precise, but this is the idea. Okay? And then if this is if the form of the reduced density matrix is somehow like the reduced density matrix of the global Gibbs density matrix, then you can also ask what the entanglement of this reduced density matrix is. Okay, so the initial state, as I said, was very simple. It was just some product state. So my initial state, so the entanglement at time 0. So entanglement, say at t equal to 0 is just 0 because I started with the product state. But at very late times, you see that the reduced density matrix is the Gibbs density matrix. And the Gibbs density matrix has an entanglement that scales with the volume of the subsystem. One way to see this is again to set just beta equal to 0. And what you will get if you compute the entanglement is, so this is entanglement at late times. This is proportional to the volume of the subsystem. Okay. Yeah. No, I think, yeah, so for concreteness, let me just take this to be small while taking the full system to be large, right? And so the entanglement, if I plot this entanglement as a function of time, so there is some growth here, and then this saturates to something that is proportional to the volume of the subsystem, right? So this is just some phenomenology of systems that thermalize. Okay. All right. So then I think I should be more specific of what kinds of Hamiltonians does this phenomenology hold. And in fact, we should exclude some Hamiltonians that almost all Hamiltonians we have heard in this conference. So if your Hamiltonian is a commuting projector Hamiltonian, so for example, the toric code or the X cube model. So this has too many symmetries, like the Hamiltonian was, say, the toric code was basically a sum of Pluckett and star terms. And all of these commute with each other. So it's almost like each of these terms commute with the Hamiltonian itself, right? So it has too many symmetries, and in fact, all of this would break down. So yeah. 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 Yeah, so your final state would be just some complicated state in the Hilbert space. And then that complicated state will have volume law entanglement. So it's more than just long range in the sense of ground states. Like this is really, your state is super complicated. Like you have entanglement everywhere. Right? So it's proportional to the volume of the subsystem.
The entropy be always interpreted as entanglement because, after all, in classical statistical physics,
yeah,
high temperature states have a lot of entropy that is of purely classical origin.
Right.
So is it still, I mean, direct proof of entanglement, this large thermal entropy? And how can one distinguish the thermal part of the entropy and the purely quantum mechanical one?
Yeah, so I think that's a good question. So for strictly speaking, like this is a mixed state, and you're asking about like entanglement entropy of the mixed state. So the measures that you use are completely different, like negativity and so on. So there you can make a distinction between what is classical and what is quantum. But here I'm just not talking about the mixed state directly. I just have a time evolved density matrix, and then asking about the reduced density matrix of that, right? And so it is still sort of pure state dynamics.
Okay. Regarding this growth of entanglement, comment on what is the time scale that it requires to reach this phase limit type of thing. And
yeah, so here, so you can think of the, so a cartoon picture for the growth of entanglement is just that I have this subsystem A, and I have dynamics using a local Hamiltonian. And a local Hamiltonian cannot create entanglement between things that are very far away. So your entanglement is sort of being created only at the boundaries. So the time scale at which this would reach volume law entanglement is proportional to the volume itself. So this time here is something like the volume of this subsystem. So, and typically what you also find is that this entanglement growth is linear in the size of the system because it's just proportional to a constant, which is the size of the boundary. In higher dimensions, this would be linear times the size of the boundary. Yeah. Yeah. Right. Yeah. No, but this is just a form of the reduced density matrix of a pure state. Like I don't care about the distinction between classical and quantum of the Gibbs state. I'm ultimately just interested in this, and then the entanglement entropy of this is volume, is proportional to volume because it is a random state in the Hilbert space. Yeah. 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 I'm saying, okay, so maybe the entanglement entropy of the pure state of the time evolved pure state is equal to the entropy of the thermal state. If that, yeah, right. So that is the statement which I'm trying to make. Okay. Yeah. So this is volume of A. So you right, yeah. So yeah. In higher dimensions, you should be a bit more careful. Yeah. So I think it would be the linear dimension because your entanglement would grow proportional at a rate which is proportional to the boundary of A. So this is length of the boundary of A, and this would be the linear dimension. So yeah. Anyway, so yeah. So this is not the volume, but yeah, the linear. Thanks for. Yeah, but you need to divide. So in 2D, the rate of growth of entanglement is proportional to the size of the boundary, and so you need to divide the volume by the boundary, which is the linear size. Okay, yeah. So I was mentioning things we should exclude, and these are things which you have studied. So toric code and X cube, these are just way too simple. They do not exhibit thermalization, and in fact, like the dynamics of these kinds of simple commuting projector Hamiltonians are almost like just basically ground state physics. So there is no interesting infinite temperature behavior that emerges, and it's also related to the fact that these have too many symmetries. We should also exclude free fermion models or things that can be mapped to free fermions, which are things like the Ising model, xj plus 1 plus zj. So these have a free fermion solution, and again, that leads to an infinite series of conserved quantities, which, I mean, you can study thermalization of these systems, but then you need to modify things like e to the minus beta h to include all of these extra conserved quantities. And that is a whole field in itself, and slightly more complicated things are interacting integrable models, which are things like the XXZ model. Which also turn out to have, in a highly non-trivial way, they turn out to have this infinite series of conserved quantities. And it's very, I mean, they show a lot of the same behavior as thermalization, but then there are some subtleties, like in the fluctuations are different. So these would also not thermalize in the sense which I described. Okay. All right, so these, just remember that we don't want to study these kinds of things. Okay. Right. So now I can. So just again, a comment on what are the kinds of states that we are interested in. So looking at the Hamiltonian, so far you have studied ground states of quantum systems. But here, since we are interested in the time evolution, we are interested in studying the properties of all eigenstates. So e to the minus En of t. And if I start with a state which has like infinite temperature, which is in the middle of the spectrum, what that means is that if this is the spectrum of my local Hamiltonian, so typically this is the ground state, and we have been so far interested in like gapped ground states. But these kinds of states have significant weight only in the middle of the spectrum. Okay? So these are states so eigenstates we are interested in, of interest. Right? And in fact, like if you look at this kind of an expectation value, where you have psi of t, OA psi of t, the eigenstates that would enter are just basically all of the eigenstates. So you get something like En, OA, En, e to the I, En minus En times t. Right? So this is the expression for the expectation value of some local operator, and you see that you're really interested in matrix elements of this operator between all kinds of eigenstates. Sorry? Yeah, thanks. Yeah. Yeah, there has to be a CA somewhere. Yeah, so I think there is a CN, CM star here. Yeah, okay. Right, so just to, again, I don't want to give a complete lecture on thermalization, but just to introduce the main concepts. So there is this expectation value of late time observables, which can be expressed in terms of the eigenstates. But then I also said that the late time expectation values are somehow expectation values in the Gibbs state. So one simple way these two expressions can be compatible is if the expectation value of the local operator in the eigenstates itself are somehow the expectation values in the Gibbs state. Right? Plus fluctuations, of course. So this kind of a condition would lead to this kind of a condition, because you see that if En and Em are different, they appear with different phases here. So this is like a sum over phases of random signs. And it's sort of only if you look at the dominant contributions in this equation, these are only when En equals Em. So the dominant part is when En is Em. And then if you, for simplicity, I'm just, but you can work out a similar argument. Right? So just to motivate this kind of an expression, so the eigenstates itself, like if all of these terms, the diagonal terms satisfy this kind of a condition, then this equation, so this implication would follow. So this kind of a condition it goes by the name of eigenstate thermalization hypothesis, which, as the name suggests, or ETH, which, as the name suggests, is just saying that the eigenstates themselves are thermal. Like you look at expectation values of local operators in the eigenstates, they are themselves thermal. And the temperature can be determined using this equation. Okay. And so the idea is, like, even in your Hamiltonian, even though your ground state is very simple, it might be like, it might have topological order and things like that, very nice structures. The eigenstates are somehow very complicated. They're just thermal states, and they're just almost look like random states in the Hilbert space. Okay, so these are again random in quotes because they're not truly random, but they're sufficiently complicated that you can treat them as random states. Right? And this kind of a hypothesis was introduced by Srednicki in 1994. Okay. Yeah. Yeah. So the temperature for an eigenstate, if I have an eigenstate of energy En, I just solve for this equation. Yeah. 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 I mean, so beta here is determined from the initial state. So one simple way is you just take the initial state to be the eigenstate itself. And then if I yeah, so the idea is that for simple product states, the distribution over eigenstates is sort of sharply peaked at a particular energy. Of course, if you take an initial state, which is like very complicated, which is some superposition of this, and this, then things might break down. But for what you can show is that for local Hamiltonians and simple initial states, everything is kind of peaked in energy. So the temperature is well defined. So the way you do that is you compute the variance of, so something like this. And you show that this variance does not scale proportional. I think this variance scales as square root of L, whereas the bandwidth scales as L. So there are some, and with just from the assumption that this Hamiltonian is local and this eigenstate is simple. Not the eigenstates, the initial state is simple. Okay. Yeah. 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 I mean, no, En is the eigenstate. So I'm saying that, like, so the eigenstates of the Hamiltonian itself, they are kind of random states in the Hilbert space. They obey this equation with, yeah. So the E and beta are related via this equation. So but just solve for En equals trace of the Hamiltonian e to the minus beta h. Right? So whenever you want to relate energy and temperature, you use this equation, and that's the correspondence. But yeah, so beta for this talk is a complication. I'll just be working with beta equal to 0, but I just wanted to give an idea of what happens in the general case. Yeah. Yeah, right. Yeah, I think so. There are these discussions of when you can weakly violate ETH while having thermalization, but I don't know. I think these are very hard to check in practice because it's all numerics. So I don't think any concrete example is known. Yeah. Mm-hmm. Yeah, I will get to that, but right now I just define symmetries as simple operators that commute with the Hamiltonian, right? So local operators, yeah. So here, yeah, these are local operators, and here you can write down, like free fermions, you can always write down local operators, and similarly for integral. Yeah, but you're getting to the point of what I want to do. Okay, so now so all of this was thermalization without symmetries, and now let's ask what happens if I introduce symmetries, right? So one thing which we have learned in basic, yeah, maybe I need this so I can erase this part. So one thing which we have learned in like basic quantum mechanics is that whenever you have a symmetry, your Hamiltonian can be block diagonalized. So a symmetry is some, so symmetry is some operator. For simplicity, it's some simple operator which commutes with your Hamiltonian. So this is the symmetry, right? And we know that whenever there is a symmetry, your Hamiltonian can be block diagonalized into quantum number sectors, which are labeled by the eigenvalues of the symmetry. So just if in case you have forgotten how this works, so this is just, you just start with a state, say I have, suppose I start with a state which has some eigenvalue Q under the symmetry operator, then the action of the Hamiltonian does not change this symmetry. So if I now consider h of psi, this is Q times h of psi, because Q and h commute, right? So you can always label your states by these symmetry quantum numbers, which are Q1, Q2, Q3, and your Hamiltonian acts block diagonally. It doesn't mix different quantum number sectors, okay? So now think of, and by symmetry, I mean, usually people restrict to kind of simple symmetries, so product of on-site unitary operators, like in the case of, say, the Ising model, you have product of Zj or product of Xj, or you consider local operators, which are like a total U1 conserved charge, which can also be expressed as an on-site unitary symmetry, okay? And some of the Hamiltonians, so suppose I choose, so I said that I should not choose the Ising model, but I gave an example of the Ising model. But you can easily imagine operators or Hamiltonians which have a Z2 symmetry, which is interacting. And just to give you a concrete example, it's something like sum over xj plus 1 plus h zj, and then you can add terms like zj plus 1. Right? So this still commutes with this product of Z symmetry, but now you break the infinite series of conservation laws that are associated with this. Okay, and similarly for U1 conserving, you can write down XXZ kind of models, but you add like a next nearest neighbor interaction, and it still has a U1 symmetry. Okay, so the point is that whenever you have a symmetry, your Hamiltonian is block diagonal. But now you see that if I start with a state which has, if suppose my initial state has a particular symmetry quantum number, this never changes under the dynamics of the Hamiltonian. So H is block diagonal, which means that e to the minus iht is also block diagonal, right? So your symmetry quantum number is conserved under the time evolution. But then that gives rise to a problem here. So where initially I said that for some initial state, if I look at expectation values of local operators, this is basically like the average over all of the Hilbert space. But then now your state is not able to access the full Hilbert space, right? So this has to be changed when you have a symmetry, right? Is that clear? Yeah. Yeah, so without symmetries, at infinite temperature, again, for simplicity, I'm just setting this, the expectation value of some local operator at late times is the average over the full Hilbert space. Like you take all states in the Hilbert space and average over them, that is the correct value. Whereas now I'm saying, so this is sort of assuming in the background that psi can access the full Hilbert space. Yeah, this is just because your state cannot access your entire Hilbert space. Yeah, then maybe it will be 0. Like, yeah. Then you will just get a 0 expectation value. But yeah, it depends on that. Now I'm starting with an initial state which has a fixed value of symmetry. Right, yeah, it lives within a block. So this is the initial state. There is some fixed quantum number. And so for such initial state, I claim that my definition of thermalization should be modified. So this has to be trace over the projector onto the quantum number sector Q divided by the Hilbert space dimension of the particular quantum number sector. So this is the notion of restricted thermalization. Okay, so this is just saying that now my states do not get out of this block of the Hilbert space, and then to look at late time expectation values, I should just be looking at expectation values of that particular, like average over the states in the restricted Hilbert space. Okay, there is actually, so there is a more sophisticated version of this, which is you consider, I mean, you might have guessed that if you have symmetries, you must go from the Gibbs ensemble to the generalized Gibbs ensemble. But I'm sort of simplifying here just for this talk. Right? So in general, you might be with the symmetry. You mean entanglement of which states? So my initial state is still simple. I just have a product state. But your final state is now some random superposition. So maybe I'll just write it more clearly. So with symmetry, so suppose I have my initial state, which is some fixed quantum number. Your final state is now a random superposition of states with quantum number Q, right? And then your entanglement really depends on how many states there are in the spectrum, which typically, if you have a U1 symmetry, you have each of these states are also kind of big, unless you start with like some extremal state. And then so roughly speaking, the entanglement grows as the log of the Hilbert space dimension of this quantum number sector. Right? Okay, so I hope that this part is. There is no guarantee that, yeah. So this is what I'm. So for U1 symmetry, you can take a block which is just one dimensional, like you just take all up spins, and then that is just one dimensional, and things. I mean, things do thermalize in that sense, but in a very trivial way, like an up spin just all ups just remains in all ups. Right. Okay. Right. Okay. Was there a question? No. Yeah, so this is sort of the simplistic version. There is a more complicated version, which I'll just note here, but I'll not say anything more about. So you should really be taking e to the minus beta h minus mu n times your operator. So this is the late time expectation value, and what I've done here is effectively set mu to infinity. And this simplistic version is sort of more useful in practice when you want to do numerics and so on. So n is the symmetry operator. So if you have a U1 symmetry, you put in the symmetry operator here. Okay, and then there is an analog of this eigenstate thermalization hypothesis for this symmetric case, where you have, so initially eigenstates were themselves thermal. So maybe ETH says that the eigenstates are random superpositions of all states in the Hilbert space. But now there is a version of that, which is just that the eigenstates themselves, I mean, this is also obvious from this block diagonal structure. If I look at eigenstates here, this is just some random superposition of states with a given symmetry. Okay, so I think, okay. Yeah. Well, what do you mean by? we are starting with a simple initial state which has a given quantum number. Yeah. Mm-hmm. No, not sure, right? Okay, yeah. So here I'm just starting with some initial state that lies in the Hilbert space and asking how it evolves. And just because of this block diagonal structure, it does not escape the block. It has a fix. Yeah, so that's the message, right? On the symmetry operators, no, I did not assume that, but I'm just giving an example where people consider U1 symmetry or Z2 symmetry or a fusion category symmetry, then you will have these blocks. It does not rely on that, and I'll get to that. Okay, so this was sort of the story of thermalization with symmetries until about 2017 or so. But later people discovered new kinds of phenomena which sort of challenged this kind of an understanding and sort of brought up questions of what do you really mean by a symmetry and how should you define symmetries and so on, which is what I will focus on now. But let me just tell you what these phenomena were, which people discovered. So one phenomenon was, it goes by the name of quantum many-body scars. And this is really work. There are many references, but first it was discovered experimentally at Harvard, and then there was a theoretical proposal also in the same year. And then parallel to this, there were also more theoretical papers. So this is Shiraishi and Mori in 2017, and myself with Andre Bernevig and Nicola Regno in 2017. Okay, so what are these quantum many-body scars? So basically, I said that all of the states in the Hilbert space, all of the eigenstates, they obey this eigenstate thermalization hypothesis. And then, so what that means is that the eigenstates should themselves be thermal, which means that the entanglement entropy of these eigenstates, so this is again the spectrum, the entanglement entropy, say I take a subsystem A, the entanglement entropy scales as the volume of this subsystem for the eigenstates, right? But then people found in these experiments as well as in these theoretical papers that there are some special kinds of states. So I'm just drawing them in blue, which violate this volume law condition. So these are very special and not ETH satisfying. Okay. So one example of this kind of a phenomenon was found in the AKLT model, but so AKLT model is what Haruki had mentioned. But I think there is a, maybe I'll not get into the details of this model, but the idea was that these set of states could be expressed in terms of some kind of a quasi-particle operator. So there is some ground state of your system, which is like the AKLT ground state, or you can take, or any other simple. So initially it was discovered in this AKLT model, and then people simplified these models to find a much simpler set of states. But the idea was that, so you have a ground state, which is some matrix product state or a product state. And then a series of states which look like some raising operator acting on the ground state turned out to be exact eigenstates. Right? And this raising operator had a local form. So this was just some sum of local operator. So Qj is some local operator acting only on site J. So Q dagger is really some kind of a quasi-particle creation operator. I'll give you a concrete example in a bit. Okay. So this kind of a quasi-particle, so yeah, this should not be confused with the symmetry operator. So maybe I'll just change notation. So there is some P dagger and this is, okay. So the point is that there is this sequence of states which can be obtained from the ground states just by applying this quasi-particle creation operator. And this, each inserting one quasi-particle into the system, as we have seen in many talks, creates some energy. So this is the ground state. This is like P dagger of G. This is P dagger square of G. And then there is a whole tower of such states, right? So inserting one quasi-particle creates some finite amount of energy, and then two quasi-particles is twice that energy, and so on. The surprise was really that such kind of simple states were actually eigenstates of a Hamiltonian, of a local Hamiltonian. And it was not obvious that there is any symmetry explanation for these states, right? So these were just some bunch of eigenstates in the spectrum, and there was no obvious algebraic structure that we or anybody else could associate with these states. So just to give you a concrete example of such states, so we can just take the SU2 multiplet of that we are all familiar with. So let's just take, suppose this is the ground state of some model or the state G, which is just all spins up. And I define this P dagger operator to be the lowering operator, so Sj minus. And so it turns out that this, so if I apply this P dagger once, so this is the G, so P dagger G is basically sum over S minus acting on this all up state, which is just one spin which has been flipped down. Right? Yeah. No, this is not AKLT. So I should make it clear. So initial discover, so this paper introduces AKLT, but then later people simplified these models. So AKLT is not as simple to explain in the talk, but there are simpler versions of these cars which have the same phenomenology, which people discovered. And yeah, I should also refer to some review articles, maybe. Yeah, so there's this whole literature on scars. So these are some review articles. So Sergej, Aban, Papich in 2020, and then one with. So if you want to read about the history, you can go here, 2021. Right. Right. So, but now I'm just giving you a simple toy model, probably the simplest model that exhibits this kind of behavior. Right. So this is like one quasi-particle. So this is what I'm calling as a quasi-particle, which is on top of this ground state. And then you can construct the entire tower of quasi-particles. So you just superpose J1, J2, and you have down, down. So these are like two quasi-particles, J1, J2, and then you can just imagine flipping one spin at a time for L of these states, right? So this is the quasi-particle tower of states. Now, I said that these appear as eigenstates of a complicated, or at least not complicated, but interacting Hamiltonian, which is expected to obey thermalization, and that Hamiltonian is just like the Heisenberg model, which would be integrable, but you break the integrability and lots of the symmetries by adding this kind of a term, which is known as the Zhayaloshinsky-Moria term. So this is called DMI for short. and this is the Heisenberg. And then you have sum over J, SZ, J. So, yeah. No, this is a sum over J. Yeah, so this is not a product state. So it's like one quasi-particle which is moving around. Sorry. Yeah. Okay. So my claim is that this Hamiltonian has all of these states as ground state, as eigenstates. So H of P dagger to the N acting on G is just N times H of P dagger N acting on G. So there is an N that appears here. So these are equally spaced eigenstates of this Hamiltonian. And if you look at this Hamiltonian, it's very hard to find what the symmetry is like. So this part has an SU2 symmetry, but then you have broken it with this term. And then there's no obvious symmetry that remains in this Hamiltonian. Okay. Yeah, for arbitrary coefficients, right? Yeah, you can also put in. Yeah, right. And the energy only depends on H. Okay. Yeah, it's nothing simple. Like, so yeah, one simple way you might have expected was if you had like a simple commutation relation, something like this, then maybe you would get, but it's not like this. So there is no there is no spectrum generating algebra, and that's part of the surprise. How do you really explain these states? Yeah, so thanks for reminding me. So so what now I said that these are ETH violating. So so what does that mean? So I said that these are not volume law entangled. So how do you see that? So this has an area law entanglement. So entanglement entropy is just zero. It's a product state. Now, if I put in one quasi-particle on top of a product state, the entanglement entropy would be something like log 2. This is an easy calculation to do. And the basic idea is like, suppose I'm looking at A and A bar between like two subsystems which are separated. This quasi-particle basically can either live on this side or this side. That is where this 2 comes in from. It's just the classical, the entropy of this classical configuration. Okay. And then if you have two quasi-particles, it turns out that these are identical quasi-particles. So you just count the number of different configurations where this quasi-particle can sit. Either both of them can be on one side of the cut. Like, so there is one where both are in A bar. There is one configuration where both are in A. And then there is one configuration where they're on either side. So the entanglement entropy is like log 3. And then similarly, if you have n quasi-particles, you can just convince yourself that it's something like log of n plus 1. So if you have an extensive number of quasi-particles, the entanglement entropy grows as the logarithm of the number of quasi-particles, which is very far from a volume law. Okay. Right. So now I try to apply my theory of thermalization, which is what I described in the first part, to these kinds of systems. And then suppose I start with some initial state that looks like all spins that are polarized in the x direction, right? And it turns out that you can, if you just look at this state, you can express it in terms of some superposition of these special eigenstates, right? So these coefficients can be easily worked out. And so if this is my initial state, the time evolution of this initial state, so psi of t, is basically just the time evolution given by e to the minus I. The energy of these set of states would come in. So you would get n times h, p dagger n acting on g. Okay. And because this is some easy kind of a time evolution, these states are all equally spaced in the spectrum. So the time evolution is really like some harmonic oscillator. And so this becomes even more obvious if you look at some expectation value or just look at the fidelity. So psi of t, psi 0, whole square. You plot this as a function of time. And this is, again, an easy calculation to do. What you find is that initially this has fidelity 1 because the overlap of a state with itself is 1. But then this just keeps oscillating, right? And it's not just the fidelity. So what this is saying is that after some time period, which is like, I think 2 pi over h up to factors of 2, the state really comes back to itself, right? And what that means is whatever expectation value that you look at, it just keeps oscillating. It doesn't saturate to what is expected by thermodynamics or the theory of thermalization, right? So these oscillations are called revivals of the state because the state sort of disappears. So the fidelity becomes 0, but then comes back after some time, and then this keeps happening. Okay. And then so sort of this was at odds with what I described earlier. So this is an initial state, which you can also compute the temperature of the state. It has infinite temperature. It satisfies all of the nice properties that I mentioned, but then it still does not thermalize, and there is no obvious symmetry explanation for this to happen. Okay, so I should also mention, I said that this was discovered both theoretically and experimentally almost simultaneously. So I should also briefly mention the experimental part, which was very surprising. So you see this kind of a behavior in Rydberg atom systems where, so just a 2-minute primer on Rydberg atom systems. So it turns out that you can basically treat this as a spin half system where each Rydberg atom is either in its ground state or in its excited state. So the two states are, this is the ground state and this is the excited states, right? And so each atom can either be in this state. So let me just call this the down state and this as the up state, right? And in these experiments, what happens is that because of some interactions between the Rydberg atoms, you can never have a configuration where two of these states are beside each other. So your Hilbert space is now constrained. So it's only consists of configuration where no two Rydberg atoms beside each other are simultaneously excited. Okay? And you can write down a free Hamiltonian which satisfies this constraint. So which means that the system can do anything provided it does not violate this constraint. And that is called the PXP model. So where the Hamiltonian is basically a projector onto a downspin at site j-1, and then it can freely flip between down and up spins on site j, and then it's again the projector onto the downspin on site j+1, which means that any atom here can sort of freely flip between the ground state and excited states, provided none of its neighbors are excited. So this is what is called as the PXP model, which they were able to sort of run an experiment with this kind of Hamiltonian. And what they saw was that, again, this kind of an oscillation, but now it's sort of approximate. There are long oscillations before the state seems to thermalize. And this length of the oscillation or the time period under which this is thermalizing was the surprise. And you should really read the reviews or the original papers to get the full story. Okay. Sorry, what? Yeah, so you can do numerics on this Hamiltonian and it shows the same behavior, but the experiment also shows the same behavior. And the experiment came first. Like they were just doing this experiment and they saw that. Yeah, I should mention the initial state that they started out with was where every alternate atom was excited, and then you start with this initial state, measure whatever you can measure in the experiment, and you see that it does not thermalize, whereas other states seem to thermalize. So again, yeah, so I should emphasize that the violation of thermalization is for this particular initial state. And it was in the experiment, it was for this particular state. Whereas if I start with some other state, everything else seems to thermalize as expected, right? So there are some states which violate thermalization, and so this was called as weak ergodicity breaking. I think some kind of a domain wall difference or imbalance, which was easy to implement. Yeah. Yeah, so if you do numerics on this, what you find is that there are, again, you can plot the entanglement of eigenstates versus energy. So I said that most eigenstates should have volume law, which is true, but then there are a few outliers which seem to be contributing to these oscillations. And these kinds of things have still not been completely understood why they're occurring, and yeah. Yeah, so this works in any dimensions actually. So you can extend this to 2D. PXP model, the 2D PXP is also conjectured to have this kind of a behavior, but it's a bit less convincing. So it's not clear. Yeah. Yeah, possibly. I don't know of any obvious. But this is really the evolution of a quantum state, so I would have to think what it really means for classical. Yeah. Yeah, so if you just look at symmetry, so the idea would be that, okay, maybe the reason this is avoiding thermalization is that there is some block. So this state maybe sits in a small block, right? This is what you would think, that this just explores this small block, and so there is no problem. But if you look at symmetries of this model, right, at least write down the obvious local symmetries, you don't find any symmetries that explain this block. Yeah. Yeah, you can make it disordered, or you can see that the translation symmetry does not explain this. Yeah. Yeah, I think it. Yeah. I think you can also put in SJ plus K. This term you have to be a bit more careful. It's not freely tunable, but yeah. So yeah, so the people have studied that. Now, off the top of my head, I don't know what happens to the scars in that case. But there is some region around PXP where the scars seem to survive. Okay, so since I'm kind of running out of time, so okay, so this is what was called as weak ergodicity breaking, at least one of the phenomenon of weak ergodicity breaking. It turns out that there was another phenomenon which seemed to suffer from the same issues, and I think Diptiman will talk more about this. So this is called Hilbert space fragmentation. But I'll maybe again just to motivate things, just give a quick overview. Hilbert space fragmentation, and this has really appeared in 2019 by Pablo Sala and Tibor, who is in the audience, et al. And also by Vedika Khemani, Nand Kishore in 2019. So this is in the quantum context. But actually, it turned out that people in this classical StatMech literature, especially Deepak Dhar and Mustansir Verma, Deepak Dhar is at ICTS. They knew these kinds of phenomena in paper in the early 90s, more coming from it turns out that there is a classical version of this, which is which was well known back then. Okay, so what are these this Hilbert space? Yeah. In the PXP? Yeah, I will get to that. So yeah, so that's sort of it's building up. Yeah. Okay, so yeah, so this classical. So yeah, it turns out that this is essentially also a classical phenomenon. So one of the simplest examples, or maybe not the simplest, but the first examples that people studied was something known as a dipole conserving model, which has Sj minus, Sj plus square something like this. Yeah. And this is a spin 1 model. Where if you look at the symmetries of this model, which are it's just the charge conservation and the dipole moment conservation. Right? And there are no other obvious symmetries, like you can also make this disordered and so on. These are the two symmetries of the problem. So again, from my earlier expectation of symmetry restricted thermalization, I would expect that if I start with a state which has a fixed quantum number of these charge and dipole symmetries, so fixed Q and P, you would explore, the state would explore all of the states in this symmetry sector, right? But you can easily see that that is not the case, and you don't even need like quantum mechanics for this. So if you just write down what these terms are doing, so I said that this is a spin 1 Hamiltonian. So there is a, so the transitions that are allowed by this Hamiltonian are something like this. So plus minus plus goes to 0 plus 0, minus plus 0 goes to 0 minus plus, and then minus plus minus goes to 0 minus 0. Right? These are the, so there is this is a 3-site Hamiltonian. So if I have spin configurations plus minus 0, it can transition to this, right? So this model is also sometimes called a fractonic model for reasons. I feel the name is a bit misleading, but the idea is like this plus and minus are like fractons, which can move only if it emits a dipole, and you treat this as a dipole and so on. But this is just nomenclature. Okay, so now I start with 3 initial states, which all have the same charge and dipole moment, and you can easily see that something is wrong. So you have states that look like this. So there is this state, there is this state, and then there is, so all of these you can compute that they have 0 charge and 0 dipole moment. But if you try to apply these rules, so this is where the Hamiltonian evolves, you see that it just does not act on these states. So there is no configuration where any of these appear. So these states are completely frozen, which is, again, I said that there are no symmetries apart from these, and so this is a bit confusing. Yeah. Possibly if you look for local symmetries, you can prove, but numerically it's easy to look for local symmetries and see them. Yeah. So those are, yeah, maybe non-local, but then that's coming to the point of how do you define symmetries, and there is a big question here, right? Okay. Yeah, so there might be non-local symmetries, which is a valid point, and in fact there are non-local symmetries, which is what I will show, but maybe not today. So right, yeah. So you will. So this is one example, and also you can see that if I just start with one plus or one fracton sitting here and try to apply these rules, you see that this can evolve to something like, so this plus can emit a dipole, and then this dipole can move away, so you can get something like this. And then there is a plus minus plus and so on. But you see that whatever you do, you alternate between a plus and a minus, right? So you can never get a configuration which looks like plus 0 0 plus 0 0 0, right? even though this is not like an explicit conserved quantity that I implemented, it turns out that there is something being conserved, which is the pattern of these plus and minus, which is, it turns out to be a general theme of these models exhibiting Hilbert space fragmentation, and I think Deeptiman will show more examples. Okay, so what's the point? So now if you look at the Hilbert space or the Hamiltonian block structure of these dipole conserving models, you find that there are really exponentially many blocks. So there are really these number of blocks scale exponentially with system size. But the symmetries do not explain all of the blocks. So if I just resolve the charge and dipole symmetries, you might get like some coarser block diagonalization that looks like this. And these kinds of blocks which exist within symmetry sectors, like these pattern conservations, are not explained by the symmetries, by the obvious symmetries of the system. Okay, so I think this all of these phenomena, so this is Hilbert space fragmentation and quantum any-body scars, as I earlier said. Yeah, I still have the diagram here. So this looks like there is one small block sitting here and a big block here. Yeah. Yeah, that's a good question. It turns out that any charge and dipole conserving Hamiltonian, even if you add longer range, preserves some form of Hilbert space fragmentation. So some of these blocks might get connected, but not all the blocks get connected. Right? Yeah. Okay. So if there are no questions, so I think many of you have already asked these kinds of questions. So there might be some hidden symmetries or non-local symmetries which sort of explain these blocks, and it does turn out that is the case, but then one has to think more carefully about how do you define symmetries. So okay, so you said that there are non-local symmetries, so let's assume that's the case. So HQ equal to 0, so I said that symmetries commute with the Hamiltonian, and let's say that these are non-local. So then there is an obvious question of how non-local you want them to be. If you just allow them to be anything, you can write down eigenstate projectors, which commute with the Hamiltonian very well, right? And but what if all of these eigenstate projectors are symmetries, then there are like the dimension of the Hilbert space number of symmetries. So it's basically saying that each of the blocks of your Hamiltonian are basically just one-dimensional blocks, which are the eigenstates of your Hamiltonian, right? Sorry? Yeah. So, but then you can try to do that. Yeah, that's a good point. So maybe you restrict yourself to the, I don't know, what basis do you want, right? So if you restrict yourself to the classical product state basis, these kinds of things cannot occur, right? This was in a basis which was sort of long range entangled. So there is a, like, whatever you try to do, it seems like there is some obstruction here, right? So obviously just making this non-local completely is kind of trivializes the whole problem. So that you cannot make this non-local. The other option was to restrict to symmetries, which are sort of which have some simple structure, so maybe on-site or fusion categories or whatever you like. But then it's very hard to search for any obvious symmetries of these kinds of models which will explain these blocks. Okay, and this is what we started thinking about with Lessig-Motrenik at Caltech. So, and it turns out that maybe I can just state the key idea and then go into more details tomorrow. So this is work done by myself and Lessig-Motrenik in 2021 or 2022. So you see here in this dipole Hamiltonian, when I found all of these blocks, I never used information of this coupling here. So I just said that there are some local set of rules which, irrespective of coupling, seems to define all of these exponentially many blocks. So what we should probably be looking for are symmetries, not just of a particular Hamiltonian, but entire families of Hamiltonians. So say I have a free parameter in my Hamiltonian, and I'm interested in operators which commute with this entire family of Hamiltonians for all values of these couplings. Okay. It turns out that this actually solves the problem. So if you define families appropriately, so what this means is that each of your Hamiltonian terms should commute with the symmetries for all values of J. Right? So I have not imposed any structure on the symmetries themselves. I just say that I give you a set of terms, which in the case of dipole would be these range 3 terms. And then I just solve for operators which commute with each of these terms. Right? And then these are the symmetries. Okay? And now it turns out that you can get more general symmetries than what than what you can dream of. Right? So maybe I'll. So I don't have much time today, but so let's see how this sort of works for the simplest of cases. So let's say now my idea is to define symmetries using the terms of the Hamiltonian rather than anything else. So let's see how this works for families of Ising models. So let's say I have xj plus 1 plus hj zj. Right? So now I want my symmetry operator. So I'm really asking what are the operators that commute with all terms of the Hamiltonian separately. So this is my entire family. And it turns out that you can easily solve for this set of operators. It turns out that there are just 2 linearly independent operators that satisfy these conditions, which is the identity and product of Zj. Right? And this is what we usually call as a Z2 symmetry. Sorry? Or the families of Ising models. Right. So I'm just saying that instead of thinking of symmetries of a particular Hamiltonian, I say that there is some family which are defined in terms of some set of local terms, and I ask what is the set of operators that commute with this entire family. Okay. And it turns out that this itself just leads to a whole nice algebraic structure of operators that commute with these set of terms. Common eigenvectors of which? Yeah, it turns out that is the representation theory of this algebras, and I'll explain that in a bit more detail, but I just want to give some examples today. So you can also do this for families of Hamiltonians. Like if you want to understand U1 symmetries in this way, you can look at families of U1 symmetric Hamiltonians. So take things like this. And then now just ask what are the operators that commute with this, and then operators that commute with all of the Zj's. And this, it turns out it's with not too much effort, you can solve for these operators. It turns out that there are L+1 operators which commute with these, and what you get are basically, so identity obviously commutes with this. Then there is the total spin operator, which is the U1 symmetry, but then you also get total spin squared and all powers of the total spin. But then it turns out that if I have more than L+1 powers, you can re-express them in terms of these. So the dimension of the space is L+1. So there are L+1 independent operators which commute with each term. And this is what we call as a U1 symmetry. So maybe I'll just close by just mentioning the general structure. So it turns out that you can define symmetries in terms of individual terms of the Hamiltonian, right? So given some set of terms or terms, local terms that define your family of Hamiltonians, you can look at operators that commute with each of these terms. And this set of operators form an algebra, which I will, again, algebra, which means that if suppose I call this set of operators as C, which I will be referring to as the commutant algebra. If I take two operators in this algebra, so Q1 belongs to C, Q2 belongs to C, then any linear combination will belong to C. Right? And also any product, which is the algebraic structure, belongs to C, and then Q2, Q1 belongs to C. Right? So it turns out that you can define everything in terms of, so there is an algebra of, so once you have operators that satisfy this, you see that operators would also commute with products of terms in this algebra. So say Hj, J+1, and say J+1, J+2. Right? So there is an entire algebra of terms of your Hamiltonian, which is sometimes called the bond algebra. And then there is an algebra of terms of operators that commute with each of these terms, which is the commutant algebra. And it turns out that if just this starting point without any reference to how the symmetry looks like, if you just start with these terms of your Hamiltonian, you can develop a theory of symmetries and irreps that will explain many of the phenomena. Yeah. Yeah, so that there is a bit of freedom there. So it depends on the family that you choose. I don't want to give up locality. So I want some kind of locality here, whether you take this to be the family or sums to be the family, it can change, right? Yeah, so you have to, if you choose a very pathological family, you might get a wrong answer. But I'll discuss more examples. Yeah. Yeah, so it is related, but they were I mean, they were working in the infinite. So I'll get to this more tomorrow. It's also related to what Frank Verstraete and Apurv talked about. It's a level of abstraction. There is a level of abstraction to go from here to yeah, I think the concept of bond algebra is the same. What they did not introduce was the commutant and then sort of looking at the commutant, right? Yeah. Okay, so I think since I've run out of time, I'll carry on tomorrow.
Thanks, Sanjay. Thanks, Sanjay. More questions.